I want to explain it to you. I want to spend a while explaining to you what I think complexity is all about. And in the process of me explaining that, goal number one is we can geek out together. We can look at some cool things with ant colonies and Conway's Game of Life, and that'll be fun. All right, and that's good. Maybe at this time in the afternoon, just geeking out is good enough. I'd like to be a little bit more ambitious, though, and suggest a few areas of application from these things we're seeing in complexity science, how we might apply that to the work that we do, both at the level of source code, how might we refactor more intelligently, how might we think about enterprise architecture differently, how might we think about human systems differently. Just 3 different areas of our work. I'd like to draw, this is my second goal, some areas, some little lines of application to our work. My third goal is a little bit more ambitious. That's really, I want to commend these ideas to you. I want to get you used to them, see if you think they're as interesting as I do, and I would like more people in the world to be thinking about them. As I said, this is an academic thing, and I know there are a few academic computer scientists who are working in this field, but I don't know of very many practitioners, people who are actually building systems who are using complexity to inform their thinking. So I'd like more people to be doing that. So that's really my goal 3, is to cast this intellectual vision. Maybe some of you will pick it up and find it interesting and do some work too. I've even got some ideas for some experiments we might run, the research we might do that could help us discover new and better ways to build systems, write code, do the things we do. So with that, those are the goals. That's what this talk is all about. You are forewarned and forearmed. Let's go ahead and talk about complexity. I'm gonna take a tour through these 5 points here. We're gonna talk about each one of these briefly. We're just gonna explore some concepts in agents and landscapes and criticality and connectedness and emergence. And I want to prepare you. It's a bumpy ride at points. Sometimes, I'll talk about agents and then we'll transition to talking about landscapes, and it doesn't feel like landscapes have anything to do with agents or criticality has anything to do with landscapes. But by the time we're done, I'm hoping that something of a coherent picture will have emerged. So let's just kind of walk through these things together and try to get an idea of what complexity is all about. And I think this long account and kind of this guided tour is much better than any sort of closed form definition could do for us. So let's just start talking about agents. Now, a complex system, or some system where this idea of complexity in this sense, capital C complexity, where this idea applies, is a system that, I'll say, by definition, is too big to reason about. You can't get the whole thing in your head. For example, a market economy. Now, you can kind of think about how a market economy is and some things that might bound its behavior, but it's not like you can predict what one is going to do, right? Not really. I mean, if you could, you wouldn't be here. You'd have retired from trading years ago and be living on an island that you own in luxury, presumably. You can't predict what sort of fashions people will be wearing. It's difficult to predict where congestion will appear in certain kinds of networks. So you can't reason about the whole thing, but as another part of the definition of a complex system, it's made up of lots of little things. The system is made up of these agents, little interactive components, each one of which we can reason about. These components interact to form the behavior of the whole system. So again, in a market economy, there are lots and lots of individual buyers and sellers, just people doing things. You can kind of think about their behavior a little bit more easily than you can about the whole economy. Maybe in a network, you can think about, well, here's what a router does. Can't maybe predict what the whole network is going to do, but I know this router follows these rules. Or let's take another example kind of from outside the technology space. Let's talk about traffic. Now, the city I live in, Denver, Colorado, United States, about 12 years ago, the governor of Colorado had this big transportation initiative, this new widening of a key highway he wanted to do, and some other things. And he did it. Okay, he got the money. He had to come ask the voters for money, and we said, yeah, okay, build that highway. If you're going to do something like that, you're going to want to tell the voters something about the highway, right? Here's this stretch of Interstate 25. That's this really troublesome corridor. It's really hard to get through there at rush hour. Right now, during peak usage, it'll take you, say, 45 minutes to get through this stretch of the highway. But we widen it. We're going to be able to accommodate so many more cars at maybe a 25-minute travel time. So in in thinking about this kind of thing, a traffic engineer is going to be probably doing something like writing differential equations. There's a rate of cars entering this stretch of highway, a rate of cars leaving leaving the corridor, and they travel at some rate. All of these, and this is just using tools that, you know, most of us learned in college and have gone on to forget. All of these tools, from 10,000 feet, kind of blurring out the idea of any individual car. They're all statistical tools that describe the performance of the average car. There's another weird traffic thing. Oh, by the way, those tools, I think, probably work well enough for that sort of thing. Predictions were made about I-25, and they turned out to be true. It's great, really. It's not so bad anymore. But some other weird traffic behavior. You're outside of the city, traveling along at highway speeds, nice and fast, no congestion, and all of a sudden, for no reason, traffic stops, or almost stops. It slows down. There's this clump of cars. You've probably seen that. You go slowly for a while, and after a while, traffic opens up again. Why would that happen? Now, the traditional mathematical toolbox that we have isn't really going to help us with that. There's no differential equations you can write that would help predict that, because you can't speak in terms of the average car anymore. You'd have to speak in terms of individual cars and how they interact. You need an agent-based model to predict that kind of thing. So you might see, what you're going to do is you're going to take these cars, put them in some space together in the simulator, give them probabilistic behavior. Some will go faster, some will go slower, and they'll interact. Okay, one car gets close to another. That car says, ah, somebody's too close, and you know, the other car feels guilty and slows down, and so forth. So the agents in this simulator interact and kind of trade information on some basis. Using this kind of a model, you actually can begin to make predictions and get some sort of understanding about why that weird clumping up on the highway thing happens. You can actually, as it turns out, observe it from the air also. And the story there is that there was a reason for the obstruction up the road in the past. Maybe somebody hit an animal, maybe there was an accident, maybe somebody got pulled over and was getting a ticket or something. That was a reason for cars to slow down. That obstruction clears, and because of the way these agents interact, the obstruction moves backward across the highway over time. It remains an obstruction for a long time. And again, you couldn't really predict that sort of thing or observe that kind of thing or experiment with that in a model without this computational agent-based model. You have to think of the pieces and their simple little bits of behavior, their simple little bit of state that they can process and model the system like that. Now, I used to be able to say in an earlier version of this presentation that it contained no code at all. Turns out that it contains some logo code, which might be unique in JAX. I don't know. We'll have to ask. You have to tell me if you've seen any other logo. Well, there's this great tool if you want to play with agent modeling of some system. Now, we're developers here, so it's not like we need help with the code, right? That's easy. For researchers, two things. For researchers who aren't developers, this is a struggle for them. And I've gotten to know some academics and some graduate students who aren't programmers, but they have to do this kind of thing. And they really struggle with the basics of development. Something like source control is you know, a deep mystery for them. So this is a nice tool to help people who aren't developers be able to write simulations like this, and to help people who are developers do all of the dumb graphics stuff. I say dumb because, you know, I don't do a lot of swing programming or anything like that. And if I were to sit down and do some simulation that I wanted to visualize, that would be 2 days of me reading through swing documentation and posts on Stack Overflow, trying to figure out how to do all that, rather than just plugging into something that's got visualization tools built in. So, neat tool here, and I'll show you a little video from it that demonstrates bird flocking. We've got a bunch of agents, all alike, that we're going to throw into this simulation. We're going to start the simulation off with them moving in random directions, all at the same speed. The birds, these agents, are going to follow these rules. The only state each one has is their direction. That's all they know about themselves. And they interact with other birds to try to move their direction to be similar to birds near them, be close to birds, but not other agents, but not too close. Those are the 3 rules that they follow. That's simple. You can think about those. You can easily code those. If we set these agents up in this simulation, again, at all random angles, press go, let the simulation run, each agent just being one piece of state, one real valued compass direction. It does something interesting after a while. The birds flock. Does that have anything to do with any actual kind of bird? Is there any bird that actually follows those three rules and no more? What's interesting and somewhat controversial about this kind of analysis is there's just no connection necessarily to reality, right? But what I think we see here is this is a cheap way to play with the rules and play with the experiments and see, and run experiments and see what sort of behavior comes out of the model, which we can then come up with ways to test against reality. It would be nice if we could do this sort of thing in software, which is kind of one of the goals I'm going towards. So keep that in mind. Now, the idea of landscapes presents us with another really compelling visual analogy for what constitutes a complex system. To get there, I'm going to talk about really a family of surfaces, 3 different classes of surfaces. Each one is going to be characterizing the solution to a problem. So we're going to think spatially about a problem. Let me give you an example of what I mean by thinking spatially about a problem. Let's take something that is near and dear recently to my heart, and I didn't even really think, I have a prop here in my bag. So there's you set on your screen in your text editor, IDE, console, a font size, right? And there's a certain font size at which you're most productive. And I've recently been asked by my eye doctor to wear these things when I'm reading or looking at my screen. I don't know what that's all about, but he said I should do it, and it really helps. So maybe you've experienced that same thing. Glasses aside, if we were to think of the independent variable here is my font size. Small font size gets bigger. And here is my productivity, how much work I get done during the day. Whatever the heck that means. I don't know how to measure that. But down here, the very small font size, I'm not very productive. As I increase that, I've found, well, I get more productive. I can see more, my eyes hurt less, I don't get a headache, and that's great. And if I make the font size too big, then I can't fit too much on the screen at once. And I have to remember more, which is another set of problems, and I become less productive. So there's kind of a surface here. So that's what I mean by thinking spatially about a problem. Now let's consider 3 kinds of surfaces that characterize the problems we encounter. Again, the third kind of surface is going to be this great visual analogy for what a complex adaptive system is all about. Now, font size is a Mount Fuji problem. That shape I just drew with my finger, it goes like this and like this. It's shaped like this mountain. It rises alone out of the plain, one global maximum, no local maxima. It's easy to climb this mountain. I wish all problems were Mount Fuji problems. This guy thought they were. This is Frederick Winslow Taylor. Is anyone familiar with the name? A few of you. Okay, well, he wrote a number of things. He wrote an important book 102 years ago in 1910 called Principles of Scientific Management. And Taylor's idea was that he was going to use scientific measurement and analysis to properly organize and optimize all human work. We're going to use science to figure out the one best way to do the work that we do. For example, if you make chairs, maybe prior to Taylor's book, you would just make chairs in the way your father taught you to make chairs. And you had some sort of workflow that was good and had some variety and gave you a good product and you were able to make a living. And he said, no, that's not good enough. We're going to send in a consultant to break that down, kind of diagram the process. You know, process consultants, they listen to you, they interview you, they diagram your process, and they say, look how crazy this is. Don't you feel silly for following this process? So here's the chair process, and the Taylorist process consultant says, oh, this is crazy. Let's simplify this. And we're going to say, well, here's how you select this and turn this leg on the lathe and cut this wood and glue this. And each of those steps, we're going to break that down into 8 distinct operations. And there are multiple ways that you could, turn a leg on a lathe. And we're going to use measurement. We're going to use science to figure out the most efficient way. Because obviously, the goal is the highest level of efficiency you could possibly discover. And so we'll kind of measure different techniques and see which one's most efficient. And that's great and potentially very dehumanizing. Maybe you live and work in a Taylorist environment. Now, not everybody calls themselves a Taylorist. In most circles, particularly like in agile circles, that's a dirty word, All right, he's Snidely Whiplash. He's got the little mustache and, you know, the villain hat and everything. Nobody wants to be a Taylorist. Maybe instead you have a culture of measurement. That's a little closer to home. Some people say that, you know. That's very much a Taylorist idea. There's nothing really wrong with trying to do the best we can, but not everything is scientifically optimizable like that. Now, a key problem in Taylor's day was, a key economic problem was the shoveling of coal. We wanted to know how to do that as efficiently as possible. All right, so he, you know, broke out some science and determined what's the right size of coal shovel. You're not going to guess, okay, you're not going to read it in Aristotle. Go ahead and do some measurement. And he did that, and he found that was 22 pounds for the average man, whatever an average man is. You know, smaller than that, and you have to move too much. Bigger than that, you get fatigued too quickly. So thank you, Fred, because that's a Mount Fuji problem. And IDE font size is a Mount Fuji problem. But decisions you make when coding, like when to extract a method or how to create an abstraction of something that you're exposing in an API, questions like that aren't Mount Fuji problems. Those are engineering problems, which are typically, I think, better characterized as mountain ranges or rugged landscapes, where there's lots and lots of local maxima that you can get stuck on. Each decision you make when building a system, say you're building a sandwich, okay, again, let's get out of software for a second, because sandwiches are easy to think about. I want you to make me a sandwich. I actually skipped lunch, so that sounds good to me. Not just any sandwich, I want the optimal sandwich. All right, I want the optimal sandwich. Now, I can't have you make all the sandwiches and I eat them and report back, because that's too many. So an exhaustive search of the whole mountain range with an altimeter is too hard. You can't do that. Yet, I also can't just say, what's my favorite kind of cheese, what's my favorite kind of meat, what's my favorite kind of dressing, and expect all of that to make the right sandwich. Because maybe I like salami because it's spicy, but if I pair that with pepper jack, perhaps the only lasting cheese innovation of the United States ever, I should say yet, I'm hopeful, we may yet do better, but pepper jack is an important contribution to human flourishing that my people are responsible for. But, you know, salami, look, it's cheese. I got to take the wins where I can get them. Salami being spicy and pepper jack being spicy, that might not go so well together. I might like pepper jack better with a mild meat like turkey. So as I make selections along this axis and selections along this axis and look at the, you know, the sandwich utility function, I'm going to see that the surface is going to be rugged because of those decisions and how they interact with one another. Sandwich building is an engineering problem. Coding is an engineering problem. I hope by analogy you can see that we define these rugged landscapes, and searching them through naive optimization, such as a Taylorist might prescribe, is a bad plan. There are other ways we have to figure out to navigate those. But a complex system, you know, frozen in time at some instant, might look like a rugged landscape. You know, maybe by analogy, again, this is the performance of my organization prior to our Agile adoption. And we say, well, we're not good enough. We're down here, and we're going to go get the Scrum training. And so we have a Scrum trainer come in and teach us the Scrum. And that's great. And we think, you know, the CTO thinks we're going to be up here now. And I just invite you to define the axes as you like. You know, this is collaboration, and this is communication, or something, and the different ways we can collaborate and communicate. And this is how much money we make for the organization. The problem is that the performance of this organization isn't a fixed thing. It's the function of these agents that are interacting. And my attempts to navigate this changes the behavior of the agents. If I say, well, every day you have to report your progress against your stated goals yesterday, that's going to change the way you behave. And every 2 weeks, you have to make a commitment with your team to get a certain thing done, or, you know, whatever the Scrum would prescribe that you do. That's going to change the way people act. So if you say, all right, we're here, now we have these new techniques, that's going to get us here, you will not end up there if that's where you stay. This is a complex and adaptive system. Your attempts to optimize it change the system itself. It's always changing under you. So there's going to be this tension now between how much time I spend trying to optimize it and how much time I spend just realizing or exploiting the optimization I've done thus far. But it's always going to be a trade-off. If you're dealing with a complex adaptive system, you will spend some time exploiting and some time exploring better ways for the system to behave, because your altitude is simply not going to stay what it is as you navigate the system. A few words about criticality. This is a property of a complex system in which it can produce some really big output for a seemingly small input. You poke it a little bit and it explodes. So just to refresh you briefly on a couple of probability density functions, here's the normal distribution or the Gaussian distribution. This is important for understanding criticality. We all know this guy, the Gaussian bell curve. There's a mean. Most of the values are clustered around the mean. And then we have the power law. The power law is interesting. Now, it has a mean. Any probability density function has a mean. But that doesn't necessarily tell us as much about what to expect from the thing. What we know about a power law random variable is that we're more likely, we're going to see lots of small values out of it. And as values get bigger and bigger, we're less and less likely to see them. Things in the real world distributed on a power law would be like death tolls in natural disasters or in wars. Most wars, most natural disasters, very small. They're over here. Some, tragically, very big. The number of inbound links to a page or a URL on the internet, that has a power law distribution. Most pages have very few inbound links to them. Most URLs do. Some URLs have many, these large events over here. But as the number of inbound links grows, the likelihood of finding a page with that many links diminishes. Continuing the analogy here, there's a dude named Per Bach. He was a Danish biologist who wrote about what he called his sand pile theory. That theory was if he just drops a grain of sand in one spot over and over and over, dropping a grain of sand, pretty soon he's going to have a pile. Apparently you can write a book on that basis, right? That's my sand pile theory. No, the important thing about the sand pile theory was that after there's a pile there, we keep dropping grains of sand. And by the way, if you try to do this in real life with sand, apparently it doesn't actually work out with sand, but with a nice round grain like rice or maybe barley, you can see this. What you're going to see in the pile is most of the time, each grain of sand is only going to cause a small disturbance. If you count the number of other, grains of rice that are displaced by each grain dropped, you'll see a power law curve there. So usually maybe just bumping one or two out of the way, but this notion of criticality is that eventually we're going to have, after these little disturbances, kind of tension built up there, and this network of connected rice grains that are just barely balancing on each other, and I drop one more rice grain, the same little event we've been seeing all along, and we see a big avalanche. That's kind of the idea. Now, another human system application of this idea is workload and thrashing. So suppose this diagram is a really super simple model of an organization. Each box is a team. Adjacent boxes, adjacent teams can share work. The number of ants in the box isn't the number of people, because that would be rude. It's the amount of work they have. And let's say each box can hold 4 ants worth of work. So here we see a box there that's got too much work. Okay, no problem, just share some with your teammate. Too much work there, that's okay. No big deal, it goes there. But obviously, bean counters who are, I was going to say obsessed, that's so negative. Bean counter is negative too. Financial professionals, or the CFO, is going to look at this and say, well, the organization's underutilized. That's not cool. So we need to make sure people have more work to do. And now dropping another unit of work on the organization is going to cause the thing to have to shuffle a lot, because we try to shift work to an adjacent team. That one little input, that one bug, that one trouble ticket, that one demo for the VP who's visiting a new customer, might cause a tremendous amount of work to be shifted around until things actually settle out. Now, it's a very simplistic model to illustrate the point, but you've probably experienced that. Perhaps you've had a job where you spend your days shifting gears all the time. You're done work at the end of the day, and you're just, you're worn out. You've been going like crazy all day long, but you're not really making progress against the goals that you're supposed to get done. I think that's probably a symptom of an overutilized organization, which leads to this, and what was I saying? which leads to this critical behavior and this experience of you spending most of your time in context switching and not enough time actually doing the work you're supposed to do. Briefly, connectedness. Why is this important? Well, if a complex system is made up of agents, and those agents can share information somehow, like the cars, sharing distance and that sort of thing, people sharing value preferences for items that they buy, classes in a code base maybe sharing complexity, that's a hypothesis that maybe we can talk about later, requires us to introduce or reintroduce a couple of terms that we learned from graph theory. One is degree. Okay, degree is simply the number of edges that a node has. That's got degree 4, or degree 5, degree 4, degree 1. There's also path length. Path length is the number of edges I have to traverse to get from one node to another. Now, this network, this graph, could characterize the agents in the complex system, the ways in which they can share information, the channels along which they can share, and we care about the functionality of that graph if we care about the agent model. We might be concerned with the way information diffuses through a network, as if, which would be the case if we were modeling a computer network. That's going to depend on path length. But I think much more compellingly, much more interestingly, is fault tolerance of the system. If the, stick with me here. Remember we had the power law and we had the normal distribution? All right, so think about that power law. If we've got a graph whose degree follows a power law distribution, that's going to imply that most nodes are not all that connected. Some nodes are highly connected. There's a small number of nodes with lots of edges, most nodes not very many, and in between it falls off rapidly, which would be like the physical internet would be an example. Also, I think most code, I've got reason to believe most code, object-oriented code, the graph of, say, those classes and their imports has this power law degree distribution. And a graph with a power law whose degree is distributed on that power law distribution is relatively tolerant to random failures. So if you disable some random node on the internet, or even random router on the internet, you're probably not going to break very much. But it's susceptible to strategic attack. If you know which nodes are highly connected and disable those, you can have a big impact. Keep that in mind. We're going to come back to that when we talk about refactoring. But first, the top of the pile, emergence, where I think all this stuff starts to come together. Emergence is a property that we see in complex systems, that we expect to see in complex systems, in which there are kind of macro-level phenomena that differ in kind from the behavior of the agents. Remember the flocking birds. The agent behavior had to do with how do I adjust my heading based on other agents near me. That was it. Where am I going to be pointed? Flocking is a different kind of thing. It would be kind of hard, by comparison, to write code that makes flocking happen. But it's fairly straightforward to write code that says, well, hey, how do I set my angle based on things near me? They're very different kinds of things. So to make that be a little bit more clear, let's look, of course, I know you're expecting this, slime mold. Obviously, everyone's favorite protist. Now, slime mold does some cool things. And I should say, under conditions of low anxiety, lots of food, no concentrated waste. Who doesn't like that? It's like this, okay? It's a unicellular thing. I was going to say animal. No. Protist. Eating, excreting, being happy. But when food gets scarce, it does this weird thing where all of these cells combine and they start to, very slowly, this is under time lapse here, engage in locomotion. No big deal, you say. You've been engaging in locomotion for the last half hour, which I have been. I walk around when I talk. But if you think about our bodies, there's all kinds of intent in them. You've got muscles and a central nervous system and tendons and all this stuff that accomplishes the goal of motion. There is no such differentiation in a slime mold. They're all the same thing. There's no tissue there. But these cells collaborate together and cause this emergent locomotion to happen. And eventually, emergent reproduction, they decide to form these little columns and spore up. And, you know, when the going gets rough, it's time to reproduce, I guess. So, a protist could do worse. Let's look at an example of computational emergence from Conway's Game of Life. Is anyone not familiar with Conway? Nobody. Good. All right. That's great. A game invented, a cellular automaton that's as fun as a game, invented by John Horton Conway in 1970. All kinds of cool things happen here. There's a set of 4 rules that determine, by the way, you divide the world up into this grid, briefly, and from iteration to iteration, we use these rules to determine whether each cell lives or dies. If you're too crowded or too lonely, you die, and there are rules under which you stay alive or come to life, if you have just the right amount of company. So, I used a very, very cool Conway simulator called Golly, which is available on SourceForge. Remember SourceForge? Yes. Golly.sourceforge.net. That's not in the slides. And I strongly caution you to set aside about 4 hours of uncommitted time before you download Golly, because you will blow the time. This thing is awesome. There's so many cool things in here. But with Golly, I said, all right, fill that rectangle with half-living, half-dead cells. Press the button, and let's see what we get. And we get this kind of seething thing that looks like a petri dish in time lapse or something. And that's what Conway does. There are all kinds of neat things happening in there. And it eventually kind of reaches a quiescent state, which most random maps are going to do. Not all that cool, right? It's not like I saw the meaning of life there. But what did I see? Some things that are worth pointing out. For example, let's look at those little guys leaving the burning spaceship there. Those are called gliders. The gliders move. There's more than one kind of glider in Conway, but it's very easy to see these as an emergent property of a random Conway board or Conway map. If you were to look at how they work and study each iteration, you'd see that they are simply following the rules. We get this diagonal locomotion happening. You can get ones that go straight, and there are other things you can do. But these just kind of happen. There's nothing intentional in the rules about locomotion. It's not like I was doing a HTML5 canvas talk and making a little Tim head bounce around the canvas or something like that. I mean, that would be intentional. I'd be coding that. But here, that locomotion is purely an emergent property. Kind of cool. And this really does look like escape pods leaving a spaceship. I like it. But more Conway. The neat thing about Conway is that it is computationally complete. So anything that a universal Turing machine can do, Conway's Game of Life can also do, can also compute. Which is a bit surprising, right? Because, you know, if you ask me what a computer is, I've been trained to believe this is a computer. A von Neumann machine is a computer. Conway, I mean, where's my Conway compiler? That doesn't even make sense. Now, it turns out there are some tools that have been developed called metacells that are like mildly programmable, and people could do some neat things with them. Like this. Here's the innards of the corner of a metacell. You can see some more. Oh, no, I'm getting ahead of myself. That's not even a metacell. This is, let me speed this up. Yeah, that happened. That's a crazy person. Okay. Here's the innards of a metacell. Looks like a factory or something, and there's these oscillator structures. That's an oscillator. See, this is a glider gun, and those gliders are getting eaten up. And if you zoom out, really watch what's happening here. There's that so-called metacell. There's another little counter structure over there that's spitting out gliders and wrecking them on that little thing. Keep zooming out, what you get is counter. Yes, you can do that with Conway. That's insane. All right. No, not especially emergent, but we'll come back to that. Some biological emergence, something we can actually look at. Some entomologists loved ants so much they filled a colony with concrete and then excavated it like archaeologists. And you see this amazing structure, really beautiful. These chambers built to, in some cases, care for young, dispose of waste, cultivate fungus, angled passages optimized for ventilation between these things. And there's really no coordination between the actors, as far as we know. They're following, and I think ants have, or rather don't have, all that rich of a mental life. I think it's probably an achievable problem of biological engineering to reverse engineer an ant nervous system and really understand them on a computational level. I'm skeptical of that project in the case of human beings, but ants, I think we can get there. And understand, I spit out this pheromone signal, I get this one in, I dig this hole, I go find food, that's just kind of how they work. Yet, we can get this compellingly beautiful structure out of them. Out of that as this, ant colony as emergent property of worker ants. Pretty cool stuff. So, I think emergence is a thing to be taken very, very seriously. We see it in Conway. I think we see it here in ant colonies. But maybe we shouldn't expect, like Skynet, to emerge from the internet. This is a philosophical opinion. I think that's unlikely. Microsoft Word isn't an emergent property of a von Neumann machine. And the counter didn't emerge from Golly. Somebody had to build that. But things did emerge. And that's a potentially powerful aspect of the systems we create. I'd like to figure out how to harness that rather than get in the way of it. What is emergence we can find in our complex adaptive systems that we work with, and when can we use that to our advantage rather than trying to stifle it? So let's take a look in our few minutes remaining at how we might apply this to our work. We might think again about human systems. And by the way, here, I said at the very beginning, I wanted to talk about human systems, big scale out there. I wanted to talk about enterprise architecture, and I wanted to talk about code on the level of refactoring. I want to suggest some areas of application that we've learned from what we've learned about complexity here. So I have an opinion about the freedom of the will, and I think this opinion is conditioned by my status culturally as a person of the West, a person of the United States, and particularly a person of the Western United States, where I come from. I think the geography is just sort of amenable there to this rugged individual sort of idea. And I think I'm at my best sort of when I'm at my most independent or most rebellious. That's like awesome, Tim, as far as I'm concerned. And I'm not just saying that. Okay, it's really true. That's really, I think, when things are the best. And if I were to apply that radically free will idea to the decisions other people make, like the guy who always breaks the build, I would have to conclude that he's breaking the build on purpose. He's deciding to be irresponsible, presumably just to rankle me, just to make me mad, right? Well, I don't know. I think he is free to decide whether, my opinion, he's free to decide whether he's going to break the build or not. And these ants are somewhat free to decide what they do, but really not so much. I mean, they just kind of follow these little computationally simple things. And I would hate to compare people to ants, but these ants, if I wanted them to, could build me a swimming pool. They have the capacity to move earth. They could dig out a hole and I'd have a nice muddy in-ground pool, or they could build me a berm and have a muddy above-ground pool. But they're not going to do it by me yelling at them to do better. All right? And often the build breaker, he doesn't seem to respond to me yelling at him to do better either. So the insight here, an insight into human systems that we get from the idea of an agent model, is how are we behaving like agents? Now, maybe at our best, we can decide with some sort of freedom on principle what we're going to do. But do we? I mean, am I more often responding to other little inputs in the system I've adapted myself to? I'm a part of this complex adaptive human system I'm working in, and there's this guy over here who also is, and he feels the need not to run the tests before he checks code in. Well, how is that a part of the equilibrium he's established with the system? And rather than yelling at him to do better, how might I look for the levers in the system that I could move, not to manipulate him, but simply to make it easier for his default mode to do the right thing? Think of the behavior of people and the decisions of people as their own adaptations to their status as rule-based agents in this system. Don't go too far with that, okay? I don't think that you want to manipulate people as computationally simple things, but there's a sense in which we often are. Now, when we build, we put on our software architecture cap, we often create diagrams that look like this. And there's some software architect somewhere who thought he was really amazing having done this, he or she. You know, when ants do their emergent thing, they build these beautiful and simple structures like this. Well, I can't spend a lot of time on this, but I can suggest that maybe there are approaches to enterprise architecture that we take that resist emergent behavior in the architecture, and others, they resist it by saying, we need to design everything in a strict way from the top down. We need the contracts that our services follow to be defined by the distinctly non-omniscient enterprise architecture committee, and everyone will follow those. Versus, we could design, say, a properly RESTful system in which, yes, contracts are specified, but the way services interact is also able to support some emergence in the use of the system. Now, I have to actually code every service I deploy. Whether I decide to use SOAP or REST, I have to write software that follows some contract. But how is one service going to interact with another if I pick some rather rigid protocol like SOAP? That's not clear that new modes of interaction can evolve. If I pick some rather more flexible architecture like REST, well, there's lots of emergence that's possible, like all of the different kinds of things on the web, which is a RESTful system. That's a very brief treatment. What I would recommend that you do is, don't listen to me about this, but read this book by as I was saying, read this book by my friends Jim Weber and Ian Robinson and their colleague Savas Parasitidis. That's a good account of REST. They're not thinking about complexity and emergence, but if you study this stuff, or even just read some of Jim and Ian's slide decks that are still floating around on the internet, think about how such an architecture might support emergence in the enterprise rather than actively resist it. Remember the rice pile, and remember criticality, remember the power law distribution, all that of nodes? Well, let's bring that to code. And this is really easy to talk about in Java terms, just because Java is an object-oriented programming language. Afferent coupling. This is a metric I need to introduce you to briefly. Afferent coupling is basically a measure of how important a class is in the code base. How many times is the class imported in the code base? That's basically, in Java terms, what afferent coupling is. How many other classes use me, either by an implicit import in the same package or an explicit one from another package, all right? So you can go through your code base, measure afferent coupling of every class. I just got thinking, a couple years ago, I started poking around at this stuff, and I thought, well, you know, I could measure that. I downloaded the CKMJ metrics suite, and I ran it on some projects. And I thought, I wonder, clearly, you know, the classes, the code base forms a graph, and one class calling another, that call is an edge, or importing another, that's an edge, and each class is a node. What would it mean if there was a power law there? So I grabbed some open source things, and I said, well, you know, maybe I can find a hidden power law in those things. I thought, all right, here's the histogram of afferent coupling in the Grails web module. Interesting. Here's Hibernate 3. Okay, here's Spring 3 core. All power laws. I was giddy. I emailed a bunch of my friends. Like, yes, there's power laws. It's great. And I went to bed. I was so excited. It's sad, I know. It's the kind of person I am. But I woke up in the morning, and I thought, wait, what does that mean? That's got to mean something. And then I remembered this whole idea of what we call a scale-free graph, or a graph with this power law degree distribution. Here's actually a practical tip for you, I think. Given that such a graph is tolerant of random failure and susceptible to what we call strategic attack, maybe this is advice for how to add tests to a legacy code base. When you inherit an untested code base, the first thing you want to do is take 6 months off to add tests to all of it, right? Number one, no, you're not allowed, ever. Number two, I'm not convinced that's a good idea anyway. I have sort of seen that done once, and the tests were not things that helped the code change. They were things that kept the code from ever changing. It was like soaking it in epoxy and letting it set. It was a bad deal. So I don't know if I would trust myself with that kind of an effort. But hey, you still need to evolve the code. You still want to have tests. So maybe you want to look for the highly coupled classes and add tests there first, because probably it's most likely that bugs there are going to have an effect elsewhere in the system. Now, I would expect if we actually took large amounts of data on lots of code bases, that this wouldn't hold up perfectly. My guess is there'd be some second-order effects. In other words, some relatively uncoupled classes that still caused significant bugs. But the biggest impact I'm going to expect from those most highly coupled classes. So that's just an idea of where you might go to start with that we get. And that insight comes from what we've learned in complexity. Now, I have just about 2 minutes left. I want to give you an idea of some research that I'd like to do. Now, it's been about a year that I've been thinking about this. I have not had the time to make this happen. So here's the deal. I can do static analysis, just some goofy metric like cyclomatic complexity of a code base. That's cheap and easy. All right, Java code, cyclomatic complexity, boom, here we are. Now, here's what I'd like to do. A couple of things. I need a visualization, maybe a 3D visualization of the code base and its complexity. And we need to be thinking of the code, again, as a graph. So maybe let's lay out the code as a graph. There's algorithms for that, the simulated annealing thing for shaking up the graph and making the layout look all pretty. Lay out the code as a nicely arranged graph, and then maybe stick like a dowel, virtually speaking, on each node to see its complexity and kind of drape a cloth over that. So we've got this surface over the graph, visualizing the complexity. Now that's just one version of the code. I want to go through the whole repo, easy if it's in Git, right? And do that same thing at each commit. I'm interested in seeing how complexity moves around in the code. Now, I don't know the answer. I haven't seen the visualization. What I'd like to know is, what does that look like? Number one, it might be cool to look at, like show it at raves and stuff. That's good. But what if there are rules? I'm interested in discovering, can I then create an agent model of a code base that causes those same effects without there being any code, but with the agents following, these 5 rules that we invent, that we infer from watching these things. This is all totally speculative and exploratory. It's not confirmatory sorts of research. This is, hey, let's go play with these things and see. But imagine if I had done that and I was able to build that agent model and I knew what those 5 rules are, and I was giving a talk on those 5 rules instead of all this complexity stuff. You'd listen to me. Those would be rules for how we can actually be better at making less complex code, or less whatever, or more whatever, be better at the practice of developing software, and all of that would come from this field of complexity theory. It's just an idea. I'd love to see that happen. I'd love to see you come up with more ideas based on things like this, and that, again, is kind of my vision casting angle here. I'd love to get this stuff into your head. I want you to take the ball and run with it, because I know more of us thinking about this is always going to be better than few of us. So thank you very much for being here. Have a great rest of your afternoon.